Here we are going to develop an algorithm of Newton-Raphson to solve the equation cos of x minus x equal to 0. And it's going to be an iterative procedure in which we will start with an initial approximation. So in Python, I first import the library, import numpy as np, and then I define a function. So I define f of x function. So this function should return a value x minus numpy cos of x. So it's up to you that you can write a separate line. For example, you can say the value, or you can say a equals and then return a, right? Then I define another function, define f prime of x. So with this function, I can say a equals 1 plus numpy sine of x. And then I say return a. This is the end of this function, right? Okay. So I require the numpy, even though in this algorithm I do not require the vectorized sine of x calculation. I can simply import the math library. So I can say math.sine of x, because for single value, that library is also available. Okay, in the Newton-Raphson's algorithm, we have to start with the approximation. So I say x old value. For example, I start with 0.4. And we generally define a tolerance level. So tolerance level 1 e raised to the power minus 3. And what I would like to compute, I would like to compute a new value. For the time being, say it is 0, or it's fine if you define it in a loop. So x new value will come from x old minus f of x old and divide by prime of x old, like the real mathematical expression. So I'm not saying xi and xi plus 1, because that would be difficult to write in the with these variables, right? So x old and x new, right? So, and if the x old and x new are closer to each other, so we can say we must stop. So we can compute an error. So numpy absolute of x new minus x old. We have to repeat this calculation again and again. And if the error is less than or equal to the tolerance level, in that case, we would like to stop. So we can say break. This is to end the loop, right? And else we would like a new calculation. So we say x old must be set to x new, and then finally there would be no and if is required. It is just determined with the structure. So this is the calculation. So I write here the loop structure. So for iterations I in range, so say a lucky number, for example, 50 iterations, right? So we will wait for 50 iterations at the most. If at the end of the program I is 50, so we can say this is not the fine thing. So the for loops in Python requires the indentation. So I have indented everything. And then this is the end of for statement, end of for loop, and this is end of if. So I write these statement in this way. to recall myself that in other programming languages, there must be the definite end of the end statement of functions. And I leave the blank lines. So let's see the final answer. So I print new value. So for the time being, I just use the primitive print statement. X new, and to confirm, I say whether it was solution or not. So whether at this x new and x new, the function value is exactly 0 or not, x new, right? So two outputs. And also, if the break was successful, so I write here the number of iterations performed, how many iterations this has been done. So if it is with the ith value, and in Python the index starts from 0, therefore this value should be I plus 1. Actually, it has performed I plus 1 iterations, right? So no confusions, nothing. As a tribute to Professor Walter Lubin, I would say no cry, no sigh, no coughing, no whistle. Behold, we are going to expect Dottie's number starting from 0.4. So we have approached 0.7390851. Oh, and this is wow. X new is not equal to 0. X new is 2.78. Oh, this is a very large number. 10 raised to the power minus 8. It's smaller one. It's smaller one. Practically, it is 0. So let's check Professor Dottie's number with a different one, as the claim was very huge. No matter you start with a number, whatever number, it will bring that one to 0.73 number. So I have selected a weird guess. Even though in practical programming, the weird guess are not encouraged. In 8 iterations, it has approached to the level, and the function value is 0. So I am convinced. Let's see, when you appreciate the Newton-Raphson's method, its power, and test it.